Okay, Assalamualaikum warahmatullahi wabarakatuh. Selamat petang.
Waalaikumsalam warahmatullahi.
Okay, so dah 28. So I think we can start our lecture now. Okay, so basically today we will start with a new chapter. So in chapter 2, we have learned on the amplitude modulation, and this week we will cover on the chapter 3, which is angle modulation. Okay, so when we talk about angle modulation, angle modulation, it actually consists of two, which is the frequency modulation and also phase modulation. Okay, so frequency modulation is as FM, phase modulation is PM. Okay, so these two modulation falls under the angle modulation. Okay, so this is basically the sub-chapter that will be covered in chapter 3. So basically today we will cover until chapter 3 part 1. So chapter 3 part 1 is until the this one 3.4. Okay, modulation index and percent modulation. So basically chapter 3 we will cover in 3 parts lah. Part 1, part 2 and also part 3. Okay, so now let's directly look into what is exactly angle modulation. Okay, so in the previous, in chapter 2, you have learned on the amplitude modulation. So I hope that you already understand how the process of amplitude modulation. Okay, so it is actually the process of changing the amplitude of the carrier signal with respect to the modulating signal. So similar for frequency modulation and also phase modulation. So for phase modulation, it is actually the process of changing the frequency of the carrier signal with respect to the modulating signal. For phase modulation, it is the process of changing the phase of the carrier signal with respect to the modulating signal. Okay, so in chapter 2, this one we have covered in chapter 2, amplitude modulation. So this amplitude modulation have its own advantages and disadvantages. So over here you can see that the advantages of amplitude modulation you have learned in chapter 2 is that it has noise reduction, it has improved system fidelity, and use low power, okay, compared to angle modulation. But this amplitude modulation still has its own disadvantages. So example is that it uses wider bandwidth and it utilizes more complex circuit. Okay, and basically angle modulation, it is used extensively, especially in radio broadcasting, television, microwave, and also satellite communication system. Okay, so now let's look into angle modulation. Okay, so this equation over here, equation 1 here, this is the equation for the angle modulated wave. Okay, so you have the modulator, same as AM, we have two inputs to the modulator. One is carrier signal, the other one is modulating signal, and the output here in the amplitude modulation, we name the output as VAM. Okay, but in this chapter 3, for the output we name it as MT. Okay, MT. So MT is the angle modulated wave. Okay, the signal that already been modulated. Okay, so why we use MT? Because angle, this is general, yeah, because we know the angle we have FM and PM, but to represent angle in general we use MT. Okay, so this equation for MT is VC cos omega CT plus theta T, where VC is carrier amplitude, carrier voltage, cos omega CT, omega C is the carrier radiant frequency, and theta T is the instantaneous phase deviation. Okay, so if you look at here, this theta T is given by this equation, equation number 2. So theta T is equals to F Vm sine omega mt. Okay, so if you look at these two equation over here, okay, you can directly know that for angle modulation, the output here, the angle modulation, the modulated wave, the amplitude is fixed, VC. Okay, the amplitude is not varies, it is fixed. The ones that is varies is the frequency and the phase, which we call as the angle. This one, this part over here. Okay, so the angle of this angle modulated wave is affected by the modulating signal. So that's why you have theta T equals to Vm sine omega mt. It is actually affected by the changes happens in the modulating signal. But the amplitude is fixed. Compared to the amplitude modulation, the ones that is varies is the amplitude. Okay. So this is what I've explained to you before. For frequency modulation, the one that is varied is the frequency of the carrier. So it is varied directly by the modulating signal. But for the phase modulation, the ones that is varied is the phase of the carrier to directly by the modulating signal. Okay. Okay, and this is also I already told you before for FM and PM. Okay, the frequency variation is directly proportional to the amplitude. Okay, look at here. The frequency variation of this FM is actually proportional to the amplitude of the modulating signal, not the frequency. The frequency of the carrier is changes proportional to the amplitude of the modulating signal. Okay, not proportional to the frequency of the modulating signal. So this is the keyword over here. Okay, the ones that is changes is the frequency varies follows the amplitude of the modulating signal. So same for the phase modulation. So the phase variation is directly proportional to the amplitude. Okay, so apa yang mengubah, dia follow apa? Dia follow amplitude of the Vm. Okay. So this is the figure of an angle modulated signal in frequency domain. Frequency domain is the frequency spectrum. If you still remember your frequency spectrum, something like this. So this is your frequency spectrum. This part over here, this is the frequency spectrum. Okay, this part over here, this is the sine wave in time domain. Okay, so this figure actually wants to show you that how the frequency of the carrier signal is affected by the amplitude of the modulating signal. So if you look at here, this is the angle modulated signal in frequency domain. So you have FC signal in the middle, carrier signal, and over here in the lower side frequency you have Fc minus delta F, and over here is Fc plus delta F. Okay, so in between here you know that the gap here is equals to negative delta F, and over here from Fc to Fc plus delta F, the gap here is equals to positive delta F. Okay, so if you look at here, the gap here is directly proportional to the amplitude of the modulating signal. So this is the modulating signal. It is a sine wave, Vm sine 2 pi fmt. Okay, so it follows the amplitude of the modulating signal. So it means that if the modulating signal is the amplitude of the modulating signal is increased, for example like this. Okay, so this upper side frequency will also be increased. Same for the lower side frequency. Okay, so this is what it means by the frequency of the carrier changes varies proportional to the amplitude of the modulating signal. Okay, so over here stated here, the magnitude and direction of the frequency deviation is proportional to the amplitude of the modulating signal. Okay, so this is for frequency. This figure over here shows the angle modulated signal in time domain. Okay, time domain means that it is with respect to time over here, time. Okay, so over here, this statement over here state that the phase shift is called delta theta. Okay, so this shift is also produce a corresponding change in the frequency known as frequency deviation. So you can see that over here, delta theta and delta F has a relation to each other. Okay, so frequency and phase, dia ada hubung kait. Okay, so if delta F change, then delta theta will also changes. So if you look at here, for the phase modulation, it also affected by the amplitude of the modulating signal. Okay, so for phase modulation, we'll look at the phase deviation or the phase shift. Okay, so I hope that you know what is phase shift. I think you have learned it in the previous subject before this. Okay, so phase shift, if for example you have two signals, so the phase shift between the two signals is what we call as the phase deviation, delta theta, this one. Okay, so this is signal 1, this is signal 2. Okay, so the phase shift between signal 1 and signal 2 is what we call as delta theta. Okay, the phase deviation. So you look at here, this is the sine wave for the modulating signal. So you can see that the delta theta is proportional to the amplitude of the modulating signal. So it means that if you increase the modulating signal amplitude, so you like this, for example, then your phase shift will also be increased. Okay, and we can actually calculate for the peak-to-peak frequency deviation, which is delta F peak-to-peak. Okay, so you can calculate delta F peak-to-peak if you have two signals like this. Okay, and you measure the time T max and also the T min, time for one cycle. So this is the time for one cycle for signal 1, and this is the time for one cycle for signal 2. Okay, so because this one is bigger, so we is defined as T max. This one is T min. So 1 over T min minus 1 over T max, you will get the delta F peak to peak, which is the peak to peak frequency deviation. Okay, so and then next, when we deal with frequency modulation and phase modulation, there are several terms that you need to know. Okay, so the first term is the instantaneous phase deviation. Okay, so instantaneous phase deviation is defined as theta t. Okay, theta t. So since it's the phase, the unit is in radian. For instantaneous phase, it is omega ct plus theta t. The unit is radian. But for instantaneous frequency deviation is defined as theta. You have a semicolon here. Theta semicolon t. The unit for frequency is hertz, but over here is radian per second. For instantaneous frequency is omega c plus theta semicolon t radian per second. Okay, so what it means by this semicolon over here, it is actually means that is a first derivative. Okay, it is the first derivative of the instantaneous phase deviation. Okay. Okay, so this one is just to state that for PM angle modulation, which is the theta t, is proportional to the amplitude of modulating signal, and for FM, the angle modulation, which is theta semicolon t, is proportional to the amplitude of the modulating signal. Okay, and over here you can see that in equation 8 and equation 9, this theta t, okay, for a modulating signal VMT, this theta t is given by k VMT radian. Okay, and theta semicolon t is k1 VMT radian per second. So these k and k1 are a constant, constant value. So this one, so over here, this is the equation for the modulated signal. Okay, MT. This is the modulated signal. This one is for phase modulation. This is for the frequency modulation. Okay, so previously you already know that the general equation for angle modulation is Vc cos omega ct plus theta t. Okay, so now from the previous equation, you know that theta t is equals to k vmt. So that is why you have k vmt cos omega mt over here. Okay, because your vmt is equals to vm cos omega mt. So basically, this equation 10 here, this one, is the modulated signal for phase modulation. Okay, so you need to remember this one, this equation 10. For frequency modulation, you already know that this theta semicolon is the derivative of theta t. So that is why theta t is equals to the integral of theta semicolon t. Okay. So your angle modulate is the modulated signal is will become mt equals to Vc cos omega ct plus, this is theta t, so it becomes integral theta semicolon t. Okay, and then you put in the value for kVm, so it become Vc cos omega ct plus k1 Vm cos omega mt dt. And then when you integrate this part, you integrate the Vm cos omega mt, your equation will become Vm over omega m cos change to sine omega mt. So your full equation for the modulated signal for frequency modulation is Vc cos omega ct plus k1 Vm over omega m sine omega mt. So this is the equation for the modulated signal for Fm. Okay, so these two equations you need to remember. This is for PM, this is for FM. Okay, so this table over here is the summary of the previous slide that I just showed you. So if you look at here, this is the summary for the equation that you will be used for this chapter. For phase, okay, for phase modulation, it is Vc cos omega ct plus kVmt. For frequency modulation, it is Vc cos omega ct plus k1 integral of Vmt dt. But this one is if the Vmt is equals to single value. But usually in real application, your modulating signal is of course is a cosine wave. Okay, so if your modulating signal is Vm cos omega mt, then your phase equation, phase modulated signal will become Vc cos omega ct plus kvm cos omega mt, while for the frequency, the modulated wave for the frequency is Vc cos omega ct plus k1 Vm over omega m sine omega mt. Okay, so these are the two equations that we usually use. Next, this is the waveform to show you the difference between frequency modulation and phase modulation. Okay, so these two is the input, this is the output. Okay, so your input one is the high frequency. Okay, so you should know that if the signal is of high frequency, then you should know that this is the carrier signal. So this one, you can see that this is low frequency, then you should directly know that this is the modulating signal. Okay, because carrier signal is high frequency, modulating signal is low frequency. And this is the output. Okay, so this is the signal for this one for FM, this one for phase modulation PM. Okay, so you can see the difference over here. For FM, the maximum frequency derivation occurs during the maximum and negative peaks of the modulating signal. So you can see that the maximum deviation occurs during the maximum positive and negative peak of the modulating signal. Okay, different from the phase modulation, you can see that the maximum frequency deviation happens during the zero crossing. Okay, this is the zero crossing. Okay, so maximum deviation happens during at the zero crossing. Okay, so these are difference between frequency modulation and also phase modulation. Okay, so this one is already stated here. For frequency modulation, the maximum frequency deviation occurs during maximum positive and negative peaks of modulating signal. But for the phase modulation, the maximum frequency deviation occurs during zero crossing of the modulating signal. Okay, so now let's look at the modulation index. Okay, so same with the amplitude modulation. So in amplitude modulation, you already know, you have learned on the modulation coefficient and percent modulation. Okay, so for modulation index, this one, it is actually the same. Okay, modulation index, modulation coefficient is the same, but if you still remember, in chapter 2 we use modulation coefficient, but actually it's the same. Modulation coefficient, modulation index is the same thing. Okay, okay, so in the previous slide you already know that for FM, sorry, for PM, for phase modulation, the modulated wave is M equals to Vc cos kVm cos omega mt, while for FM it is mt equals to Vc cos omega ct plus k1Vm over omega m sin omega mt. Okay. Okay, so if you compare these two equations, okay, with the general equation, you can rewrite this equation as in equation 12. Okay, so your equation can becomes a general equation, which is mt equals to Vc cos omega ct plus m cos omega mt. Okay, so m over here, okay, m is this one. This is the m. Okay, so that is why for phase modulation, okay, modulation index and percent modulation, for phase modulation, it is m equals to kVm. Okay, and this m also, we also define as delta theta. Okay, but the formula is m equals to kVm, where k is the deviation sensitivity. So k, in questions, you'll be given the value for the deviation sensitivity k. Okay, this is for phase modulation. Okay, but for frequency modulation, the m is this one, k Vm over omega m. This is the m. Okay, so you must remember that the modulation index for frequency modulation and phase modulation is different. Okay, for phase it is m equals to kVm. For frequency it is m equals to kVm over omega m. Okay, so based on this equation, you will get this. This one I already showed you before. Okay, so you can write your mt equals to Vc cos omega ct kVm cos omega mt, or you just write the general equation like this by using m, Vc cos omega ct plus m cos omega mt. But you should know that m is equals to kVm. Okay, so usually we remember the general equation, this one, but you must know that For FM, it is M equals to KVM. For FM, it is M equals to K1 Vm omega M or omega Fm. Okay. For this one, for frequency modulation, okay, it is M equals to K1 Vm or divided by omega M. So this one is equals to K1 Vm divided by Fm. Okay, so take note, the unit for modulation index for phase modulation, it is radians. But the modulation index for frequency modulation, the unit is unitless, no unit. Okay, so you must remember this and this and also this. Okay. And modulation index for FM also we define as delta F. So that's why we have delta F over here. So delta F or M, you can define M as delta F over FM. Okay, so from the equation for the frequency modulated wave, you have this VC cos omega CT plus K1 Vm over Fm sin omega mt. Okay, so you can also write like this, VC cos omega CT plus M sin omega mt, where M equals to K1 Vm over Fm. Other than these two equations, you can also write like this, where delta F over here, delta F is K1 Vm. So that's why we change this K1 Vm as delta F. Okay. But usually we use this one. But you need to remember this. Okay. Yang ni kita jarang guna. We hardly use this one. Okay, so next is to show you the relationship between the modulation index, frequency deviation and phase deviation with respect to the modulation signal amplitude and frequency. Okay, so previously you know that M equals to KVM and also M equals to K1 Vm over Fm. Okay, so if you look at this graph, the first graph, okay, so you can see that if the amplitude of the modulating signal increase, the modulation index will also increase. Okay, so this is valid for FM and also PM. Okay, so how do we get this? So it is based on this equation. So you can see that M here is directly proportional to Vm. Same for the frequency modulation, where M is directly proportional to Vm. Okay, but this is the graph of M with respect to Fm, frequency modulating signal frequency. So you can see that this one, if for the phase modulation, okay, the modulation index, it is not affected by Fm, because you can refer to this equation. This is just M equals to KVM. Okay, there is no Fm here, so you can know that for phase modulation, the M is not affected by Fm. But for the frequency modulation, you can see that M is inversely proportional to Fm. So it means that if the the value of FM increase, then the modulating signal will decrease. But if the modulating signal frequency decrease, the modulation index will be increased. Okay, it is inversely proportional. Okay, so next is delta. Okay, delta theta. So you can see for VM, for phase modulation, if we increase VM, then the delta theta will also be increased. Same for this one, VM. We increase VM, then the delta F will also be increased. Okay. This one is based on M equals to delta F over Fm. Okay. Okay, so table 7.2 here is the summary of the equation that we have in chapter 3. Okay, so this table usually will be given in your final exam. Okay, so basically you don't need to remember this one. So this table will be given in the final exam for angle modulation. Okay, so this one is a frequency, this is for phase modulation. So you can see this, there's a different, this is the equation for the modulated wave, and also the equation for modulation index, and so on. Okay, so this one will be given. But if your final exam is online, so I'm not sure yet whether this table will be given, because usually for online exam it is an open book. Okay, so you can refer the table anywhere. Okay, so that is for the modulation index. Okay, so for angle modulation we can also calculate for the percent modulation, but it is different compared to amplitude modulation. So if you still remember, for amplitude modulation, the percent modulation is the modulation coefficient directly multiplied with 100%. But for angle modulation, to calculate for the percent modulation, you need to use this formula. Okay, so it is percent modulation equals to delta F actual divided by delta F maximum multiply with 100%. Okay, so you cannot directly multiply M with 100% like this to get percent modulation. Okay, this is only valid for amplitude modulation. It is not valid for angle modulation. Angle modulation, please use this formula. Okay, so any question up until subchapter 3.4.3? Any question? Ataupun tak faham?
Doktor.
Faham ke tak?
Faham.
Faham, okay. Good. Okay, so this is actually the end of chapter 3 part 1. But actually I want to continue sikit chapter 3 part 2. Okay, so actually similar to chapter 2, chapter 3 also, the first part and a little bit of the second part, this one focus on the analysis, okay, calculation. But after subchapter 3.5, okay, so the rest is theoretical. Okay, fully theory. Okay, so please do expect that for the calculation part for chapter 3, it is from subchapter 3.1 until 3.5. Okay. So I want to continue with chapter 3 part 2. So the slide for chapter 3 part 2 I've already uploaded in the ULearn. Okay. Okay, so just now we have learned up until the percent modulation. So now we will continue with the bandwidth. Okay, frequency and bandwidth analysis of angle modulated wave. So if you look at here, the statement here, the frequency analysis of the angle modulated wave is much more complex compared to amplitude modulation. Okay, so the analysis is much more complex. Why? Because for the phase or frequency modulation, the modulating signal will produce an infinite number of side frequency. Okay, so therefore it has an infinite bandwidth. Okay, where each side frequency is displaced from the carrier by an integral multiple of the modulating frequency. So if you still remember, for amplitude modulation, you have the frequency spectrum like this. You only have one sideband, one pair of sideband. Okay, this is upper side frequency, this is lower side frequency. Okay, but in chapter 2 part 2 we have covered if we have more than one modulating signal frequency, okay, then you could have something like this lah. But for frequency and also phase modulation, this sideband, okay, can be infinite. Okay, dia boleh jadi banyak sangat, infinite number of sidebands. Okay, so that is why the bandwidth can become infinite. Okay. So how to determine the numbers of sideband in the angle modulated wave? Okay, so to determine the number of sideband in an angle modulated wave, you need to use what we call as the Bessel function. Okay, Bessel function. Okay, so remember this is the formula that you have learned in part 1. Okay, so this is the formula for angle modulated wave. Mt equals to Vc omega Ct plus m cos omega Mt. Okay, but from this equation, you cannot know how many frequency components are there. Okay, based on the above equation, the individual frequency components of the angle modulated wave is not obvious. Okay, so from this equation, you don't know how many sidebands. Okay, but for amplitude modulation, based on the equation itself, you can know how many sidebands are there. Okay, so in order to know how many sideband, we need to come up with a new equation based on the Bessel function. Okay, so this is the derivation. You don't you can try to derive this. Okay, just follow this and you will get this expand equation. Okay, so usually we just use this expand equation. Okay, so this one you need to remember lah. Okay, so from this equation you can know that this J naught, okay, J naught m cos omega Ct is the carrier signal. J1 is the first sideband. J2 is the second sideband until Jn. Okay. So this one stated that angle modulation produces infinite number of sideband, what we call as the first order sideband, second order sideband, and so on. Okay, and the magnitude of the sideband is determined by the coefficient J1M, J2M until Jnm. Okay, so basically for angle modulation, the number of sideband, it depends on the modulation index M. Okay, so this is the Bessel table. We call this as the Bessel table. So if you have a question on angle modulation, usually this table will be given to you. Okay, so how to use this table? You can see that over here you have the modulation index. So after you calculate the M, the modulation index, you refer to this table. Okay, and you can know how many sidebands are there. So for example, if your modulation index is 0.25, then this is the carrier. This is the amplitude of the carrier is 0.98, and you have one sideband because you only have up until J1, and this is the amplitude of the sideband. Okay, not the amplitude but the coefficient for the amplitude. Okay, for the first sideband. But if you have the modulation index equals to 2, then you will know that you have 4 sideband. Okay, and so on. Okay, so you can see that over here, as your modulation index increases, your number of sidebands will also increase. Okay, so that is why we said that that is why we said that the number of sideband for angle modulation, it is infinite. This table only shows you up until m equals to 10, but it can be bigger than 10. Okay. Other than the Bessel table, we also have the Bessel curve. Okay, so in your final exam, okay, we will either gives you this Bessel table or the Bessel curve. So this is the Bessel curve. Okay, this is also used to determine how many sidebands are there. Okay, so for example, this is the modulation index, this is the amplitude coefficient. Okay, so if your modulation index is equals to 1, then you need to use your ruler. Okay, gariskan dekat sini. Okay, and then you tengok what is the value for J0, J1 and J2. Okay, for modulation index equals to 1. Okay, but this one is more accurate lah, because the value is directly given. This one you need to estimate the value. Okay, so conclusion from the graph over here. Okay, this one I think you can read by yourself. This just summarize what you can see from the previous Bessel table and Bessel curve. So for example, you can see that from the Bessel table, later you recheck with the table, the modulation index of 0, it produces 0 side frequency. Okay, and this one I already told you before that the larger the M, the more set of side frequencies are produced. Okay, and the last one over here, as M increases, the number of significant side frequency also increases. Therefore, the bandwidth will also be increased. Okay. the bandwidth of the angle modulated wave is a function of the modulation index. Okay, so now let's look into how can we calculate for the bandwidth for angle modulation. Okay, so for angle modulation, to calculate the bandwidth, there are two ways. One is based on the Bessel function or the Bessel table. This is one method. The second method is by using Carson Rule. Okay, so there are two methods, there are two equations or two formula to calculate for bandwidth for angle modulation. So the first one is based on the Bessel table. Okay, so this is the formula for the bandwidth if based on the Bessel table. So it is B equals to 2 multiplied with N Fm. So Fm is the modulating signal frequency, and here is the number of sideband. Okay, so that is why we call based on the Bessel table, because from the Bessel table you can determine how many sidebands are there. Okay, then only you can use this formula. But for Carson rule is actually an estimation. Okay, estimation of the bandwidth for angle modulated system regardless of the modulation index. Okay, so for Carson rule, it is actually an estimation. Okay, we don't need to calculate for the modulation index, but actually we just estimate the bandwidth, and the formula is this. Okay, so this is the formula for the Carson rule. Okay, so it is B equals to 2 multiplied with delta F plus Fm. Okay, but for a low modulation index, okay, where you know that for low modulation and index, Fm is much larger than delta F, therefore you can ignore this delta F, so it become B equals to 2 Fm. For high modulation index, your delta F is much larger than Fm, so you can actually ignore this Fm, so your equation becomes B equals to 2 delta F. Okay, so this is for very low modulation index or very high modulation index. But otherwise, you just use this formula. Okay, use this formula. So if you look at here, I've already told you that Carson rule is just an approximate. Okay, it is an estimation. So Carson rule, usually it will gives you a smaller bandwidth. It will gives a narrower bandwidth compared to the bandwidth that is calculated using Bessel function. Okay, so therefore this Carson rule, even though it has a narrower bandwidth, but if you design a system using the bandwidth from the Carson rule, it will have a poorer performance compared to the Bessel table. Okay, so look at here. Okay, so even though Carson rule have a narrow bandwidth, but it has a poorer performance than the system that is designed with the Bessel table, because Carson rule is just an estimation, approximate. Okay, so this one, the bandwidth using Bessel table is much more accurate. Okay, so later you will see that if you calculate using these two different equation, you will get a slightly different answer. You will not get exactly the same answer for the bandwidth. Okay. So next is the deviation ratio. Okay, so this is the last part for today, deviation ratio. So deviation ratio is the worst case modulation index. Okay, it is actually the modulation index M, but it is for the worst case, the maximum one. Okay, so to calculate for the deviation ratio, this is the formula. It is delta F max divided by Fm. Okay, Fm max. Okay, you must make sure that the value is maximum. Then only we can say that this is the worst case modulation index or the deviation ratio. So if you don't have the max here, then it's actually just a modulation index. Okay, so now let's try and do example. So determine the deviation ratio. Determine the deviation ratio and the bandwidth for the worst case. Okay, so look at here. This is the worst case modulation index. Worst case modulation index. So meaning it is the deviation ratio DR for an FM broadcast band transmitter with a maximum frequency deviation. Okay, maximum frequency deviation delta FM max is 75. And maximum modulating signal frequency, which is FM max, is equals to 15 kilohertz. Okay, so that is why if you calculate for the deviation ratio or the worst case modulation index, it is delta FM max divide delta FM max divide with FM max. Okay, so 75K divide with 15K, you will get the deviation ratio of 5. Okay, so remember 5 deviation ratio is actually the modulation index, but for the worst case. So you should know that 5 is the modulation index. So to calculate for the bandwidth using Bessel table, it is B equals to 2N multiplied with Fm. So now you need to determine the number of sideband. Okay, so to determine number of sideband, okay, your modulation index is 5. So you need to refer to the Bessel table. Okay, refer to your Bessel table. This is your Bessel table. And look at here. So your modulation index is equals to 5. So your number of sideband is equals to 8. So you have N equals to 8. Okay. Okay, then you put in the equation. You put in this equation. So your N is equals to 8. So 2 multiplied with N multiply with Fm. So you will get the bandwidth is equals to 240 kilohertz. Okay, so the second example, for a 37.5 kilohertz frequency deviation. Okay, so this is delta F. Frequency deviation delta F equals to 37.5, and the modulating signal frequency Fm is equals to 7.5 kilohertz. So you can calculate for the modulation index. So the modulation index is M equals to delta F over Fm. Okay, so you will get the modulation index is equals to 5. Okay. So using the formula for the bandwidth based on the Bessel table. So since your modulation index is 5, of course your number of significant sidebands will also maintain as 8. So it is 2 multiplied with 8 multiplied with 705,000 is 7,500 for the FM. So you become 120 kilohertz. Okay. So you look at here, even though example A and example B has the same modulation index, but it achieves two different bandwidths. Okay, so this bandwidth, you can see that the bandwidth here is bigger compared to this one, even though it has the same modulation index, because this bandwidth, the wider one, it is for the maximum, the worst case modulation index, or the widest bandwidth. Okay, so that's why this one we call as the modulation index, we call as the deviation ratio. Okay, so this one, if we calculate using Bessel table, so what happens if we try and calculate the bandwidth using the Carson rule? Okay, so now the next one, let's try and calculate this example A, but using Carson rule. Okay, so Carson rule, the formula for Carson rule is B equals to 2 delta Fm max plus Fm max. Okay, so 2 delta Fm max is 75 K plus Fm max is 15 K. Okay, so if you calculate this, you will get 180 kilohertz. Okay, so you can see that for the same question, okay, when you calculate the bandwidth using the Bessel table and using the Carson rule, you will get a different answer. This one is 180, this one is 240. Why? Because I've already explained to you before that the Carson rule is just an estimation, and usually the Carson rule will produce a much narrower bandwidth compared to the Bessel table. Okay, so that is why in the previous slide you already stated that a system that is designed using Carson rule has a poorer performance compared to the system that is designed using Bessel table. Okay, faham eh? You will not get the same, exactly the same bandwidth. Okay, so this one, this is what I explained to you. This is the calculation using Carson rule. Okay, so any question up to this 3.6? So we have finished our lecture for today. So any question? No question faham Okay.
Faham.
Okay. So before this, I already told you that your midterm test is expected to be on 30 April. Okay. So it will cover chapter 1 and also chapter 2. Okay, only 2 chapter, which is intro and also amplitude modulation. Okay, and your quiz one, can we do it on Friday? Can we have your quiz one on Friday this week at 10? You should have class at 10, right? So can we do quiz one this week on Friday at 10 a.m. Chapter 2. Chapter 2 only.
Boleh.
Yeah. Okay, so later so I will use Yulen for the quiz and for the midterm test. So you go under the assessment. Okay, so I will put the quiz under the assessment tab. Okay, so if you don't have any more questions about the lecture or your tutorial, then I think we can end our class for today. Okay, and I think I haven't uploaded video for the chapter 2 part 2, I think. So I will upload it maybe after this or tomorrow. Okay, so thank you very much.
Thank you, Doctor.
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 Sama.